Okay, so we are going to talk about eccentricity and properties of ellipses. And if you think about um, what we're really dealing with in terms of like orbits, planetary orbits, satellite orbits, etc., we're looking at elliptical motion. So Kepler's first law actually told us, we're not orbiting in circles, we're orbiting in ellipses. Well, the first thing that we need to do is we need to look at an ellipse. So an ellipse is basically like an elongated circle, and it does have a couple key features to it. So let's get that going. Here we go. So it does have a center, and it has two foci. Now, the center is just like the center of a circle. It's the dead center of the ellipse. The foci are those points that are causing the elongation. And so what we're getting is the distance from the center to one focus is the same as or equidistant as the center to the other focus. Cool. So if we move forward and we say, let's connect all three of these with a line that extends from one side to the other, we get what we call the major axis. So the major axis is going from one vertex way over here with my ellipse, all the way through my foci, my center, my other foci, and then getting to the other vertice. Okay, well, in Kepler's laws, he actually defines something called the semi-major axis. And the semi-major axis is actually half of the major axis, semi being half. So eccentricity, which is a property from way before Kepler, but it's a property of an ellipse, eccentricity is described using that semi-major axis. And so what we're looking at is if C represents the distance from a center to a foci, then A is going to be from the center to a vertex. So the semi-major axis and the foci distance. And so if we're looking at eccentricity, eccentricity is very simply the proportional relationship of these two distances. So E will equal C divide A. So let's move forward. Let's actually get some idea of what eccentricity is and how it represents within the world of astronomy. So if we look at two cones upside down, this is what we call conical sections. Imagine we're playing Fruit Ninja with these two conical sections. If we cut straight across, we get a circle. And a circle has absolutely no eccentricity. So E equals 0 here. Now, circular orbits are very rare, but you can technically have a perfect circular orbit to an extent. You just wouldn't have any elongation. It may not be a sustainable orbit, so you got to keep that in mind. Earth has a near circular orbit, but it's near, meaning it is still elliptical. An ellipse is essentially like we're cutting at an angle. We're still keeping that elongation, that circular shape, if you will, but it becomes more of an ellipse, what we were just looking at. The eccentricity for an ellipse ranges from 0 to 1, so just above 0 and below 1. So that's our range. Obviously, as you increase your eccentricity, getting closer to 1, you get more elongation because your foci are moving further and further away. As we start going towards a parabola is going to be a very special case. It is where eccentricity is 1. Now here's what's really cool. Ellipses are kind of like planetary orbits. They're the things that are pretty much stationary within the solar system. When we're looking at parabolas, these can be visiting objects. So these can be objects from other star systems, they can be from intergalactic space, interstellar space, etc. And what we get to see is an object that's coming in with an extreme eccentricity, and then it just shoots back out. So this would be something possibly like a comet that's just visiting, not a recurring comet like Halley's Comet, for example. Halley's Comet would be an elliptical comet. But when we're looking at a parabolic orbit, we're looking at something that just flies in, goes away, and we never see it again. Hyperbolic is pretty much the same thing, but you would generally have a lot more speed to this object and very little influence from like a gravitational source of some sort. It's enough to bend the orbit, but what we're getting is not enough to trap the object, just like in a parabol. It's not enough to trap the object into an orbit around a gravitational source. So hyperboles, they have, or hyperbola, excuse me, have eccentricity of greater than 1. So when we're looking at this conical section, it kind of helps to understand the background of where these orbits really fit in with regards to the geometry. Now, let's look at an example. Let's say we're dealing with Mars. Mars is kind of, or not Mars, Mercury. I can't even read my own PowerPoint. All right, so let's deal with Mercury because Mercury is pretty cool. It's very close to the sun, has a very large eccentricity of 0.206, and it has, some other really cool properties. We're not going to go into those now. If we're using our eccentricity formula, E equals C over A, we know eccentricity, we know the semi-major axis. This is the distance in astronomical units. What we don't know is where is the center, because the sun is not necessarily the center, especially when you have eccentricity of anything greater than 0. So let's go ahead and find our eccentricity relationship. So we just plug in our eccentricity value of 0.206 and set it equal to c divided by the 0.38, the distance in astronomical units. When we pop this into a calculator, we get c is about 0.078, give or take. Now, here's what's really cool. C represents the distance from the center to one focus. But if we want to know where are the two foci, now we just have to multiply by 2. So that gives us a value of 0.16. Now you may be saying, okay, why do I need to know where both foci are? Let's assume that you're going to construct the orbit of Mercury. And you're using a scale of, say, I don't know, 1 inch is 1 astronomical unit. Where you place your 2 pins to basically graph out your ellipse or construct your ellipse is going to be the foci values. So the foci are 0.16 inches apart. That's the separation between them. All right, so let's move forward. So we know our center to focus value. We know our focus to focus value. What we need now is the semi-major axis giving us the major axis. So we have the semi-major axis of distance, that's our astronomical unit, of 0.38. When we plug in for the major axis, it's basically just twice the value. What we get is 0.76. Now you may be saying, okay, what does that mean? Well, 0.76 is the distance from one side of the ellipse to the other side of the ellipse. So it's the vertices crossing through the both foci and the center. Now, here's what's really cool. If you're constructing the orbit of Mercury and you know that your measure between the two foci is 0.16, you know where those 2 pins should be. The length of the string that you're wanting to use when you tie it around and you construct your actual orbit, the length of the string needs to be 0.76 inches. So that way it represents the actual scale of the orbit. So let's look at that. So if we're constructing our orbit, Notice I put the values for us down at the very bottom now. We have 0.08 is the center to focus to focus 0.16, and the major axis 0.76. So the first thing is we need to get our focus to focus distance and put our pens into the paper, cardboard, whatever you're using to construct. Once you have this distance, we need to measure out the major axis using that string. So we're going to measure out a piece of string. You can cut it, you can just knot it off, tie it, whatever you're using. But use a little piece of string, measure it out to the major axis distance. Okay. At this point, we're going to go ahead and use the pencil to wrap that string around both foci, pull the pencil tightly so that we have no slack in the string, and then construct our ellipse. So you have your two foci, you're attaching the string to both foci, you're using a pencil to just lightly trace out your elliptical shape. At this point, you have the ellipse and it is accurately measured. Here's the part that you gotta remember to do. You gotta remember to label things. So take the pens out. One of those pens represents the sun. So you need to label which one you're using as the sun. When you're constructing the orbits of other planets, use the same location as the sun. Don't create a new sun, okay? It also helps to label the orbit. So if you want to put Mercury on it, or if you want to draw a little planet, or both, I did both in this one. That's perfectly fine as well. So I hope this helps you as you're starting to work on those constructions for Kepler's lab. The constructions can be tedious, but follow the process. And if you need help, make sure you check out some of the other resources. Also bring the questions into my office hours. All right, catch you later, guys.